So it's not common within MIT crowds, but please interrupt me. The more you talk, the better the presentation will go. All right? So I have this reasonably ambitious title, especially in its end. So I would like to first acknowledging my research group. Some of them have graduated, some of them are still here, that this work would not have happened without their contributions. So I will talk more broadly about why multimodal AI, why I'm excited about the area. Then talk about medical applications, holistic AI and medicine. The term I have is HAIM, holistic AI for medicine. Then an application in a real world environment. I kind of doubt I'll have time for meteorology applications, but then I'll talk about implications for the future of universities that I think is important. So let's think about medicine. So all of us have some experience, either personal or from our families, going to doctors. And if you look at how physicians make decisions, they utilize scans, in this case MRI, CT scans, X-rays, language, radiology reports, nurses or doctor notes, tabular data, electronic medical records, as well as often time series of this data, as well as potentially genomic information that is increasing in the environment. So the question is, can machines use multimodal data to make medical diagnosing decisions like humans do? In agriculture, similar, let's think what this data is available. We have images of agricultural areas, meteorological data, temperature, rain, pressure, earth-related data, ground information, crops and so forth, as well as yield data. So can machines use multimodal data to make better decisions on what crops, at what time, with what fertilizers, and what antibiotics for the plants? Climate change, one of the most important challenges of our times. So can we predict the direction and magnitude of hurricanes? What has been used for the last 100 years is partial differential equation models that solve the Navier-Stokes equations, and they are currently used to find directions and magnitude of extreme phenomena. There's the so-called American model, the European model. I remind you, during the Hurricane Katrina in the mid-2000s, the American model said that the storm will go left, the European model right, and then it went right through New Orleans with catastrophic events. We have available data on images. These are pictures of hurricanes that people collect, physical data, as well as language data, global warming articles, and so forth. Similar questions. Can machines do that? Also, at least in my view, if you look at humans, the five basic human senses that people agree, maybe others as well, that people agree less, is touch, sight, hearing, smell, and taste. In other words, multimodality is a fundamental characteristic of human life. So why not machines? So this is the motivation of why multimodality might be an interesting story. So the particular work I'm going to talk about is a paper that appeared in 2022, Nature Digital Medicine, together with members of the group, on applications in medicine. So I started thinking about the first time I thought about multimodality was actually 2013, about a decade ago. And it was really the success of IBM Watson for playing Jeopardy. I was very excited by this when I saw the machine beating some of the best human players in a game that I was personally still am very poor about. I mean, I answered 5% of the questions, and the computers were answering 95% of the questions very successfully, better than humans. IBM, after that, did, in my opinion, some strategic mistakes, overpromised and under-delivered, especially in the medical area. But the idea came to me that this could be something that, as we understand better, this could be a good something to develop, particularly in medicine, because I have some aspirations on this. So the key question that I was asking, given that it's very natural to apply multimodal AI for medical applications, is how to combine the various modes. So the very first one is tabular electronic records that are naturally numeric. Right? So this is a case where we use the data as is. There's no transformation needed. Time series data is, for example, in this is, let's say, blood pressure over time. You can extract automatically features from this data. So this is a particular, the maximum, the minimum, the median, the mean, the number of peaks, and so forth. There are automatic ways to select from a time series a collection of data in the hundreds, the data that you get. Now, on this work is pre-ChatGPT, GPT-4. I'll make some comments because we also tried very recently with these new methods, and I have to admit we didn't see a significant improvement where we utilize the new information that we have. Admittedly, we haven't tried extraordinarily a lot, but here's an example of an unstructured data. The large language model we use is Clinical BERT. So we have an example in which this is a trajectory of a patient, sample event strings. There is words that relate with the treatment of the patient, and they're a patient summary. So we pass it through, we have a lot of this data. We pass it through a large language models like Clinical BERT, and in the end, let's say we want to make a prediction. We don't care about the prediction. We get about the final piece before the prediction, in which is a summarization of the signal, or in this case language, in a vector. The dimension of the vector is 768 for BioBERT, but this is an embedding that takes as input the language, and as output a vector of numerical characteristics that we don't understand, but it's a summary of what the message is, that could then be something that we will add to the other information we have, because now it's also numerical. Okay. Another example about EKGs. So EKGs, in addition to the signal itself, it's an analog signal, they also have language. So this is a particular language about the statement about the patient. Again, passing it through Clinical BERT, you also have a vector of description and embedding that characterizes that. Images is another example in which you have an image that is passing through, in this particular case, CNN, convolutional neural network, that has various stages. At the very end, just before a prediction, there is also an embedding that is also numerical. Okay? So what have I done so far? I have actually taken structured data, either directly or through a summarization through numerical procedures, and then unstructured data like images and language, in which I take this information and I put it together. So this is perhaps the, if you want to rejoin, if I lost you for a second. So this is an environment in which we have the various embeddings. We have the images here. We have various language models, time series data, tabular data, and potentially others, as you have new things happening. For example, in some medical applications, there's genomic information, so you might also utilize whatever methods you have. In the end, you have to have a numerical embedding that captures the system. Then you concatenate this. This is now your new signal, all numerical, and then you use more traditional machine learning models. Could be boosted methods. I mean, you can use various things there, but this is numerical, classical machine learning to make the final prediction. Okay, that's sort of the methodology we used. So the particular experiment is, we've done multiple, but the one I will comment today is on a data set that MIT was involved. This is data, about 35,000 records. These are patients in the emergency ICU room at Beth Israel Medical Center. And we have chest x-rays, electronic records, radiology notes, and EKGs. We have all of the above, in other words. And the objective is to predict 12 things. The reason we selected those is because they have a plurality of characteristics. All of them are related to the upper body. We would like to understand a mortality prediction, whether or not the patient dies in the end of discharge. Diagnosis, we selected 10 diagnoses. Fracture, these are all related with the upper body. And these are 10 of them. And then length of stay, which is to predict whether or not the patient leaves the hospital within 48 hours. So there's a mortality issue, there's administrative issue on length of stay, and there is various predictions. Many things else are possible, but this is an indication. So the question I'm asking is whether this multimodality here is helpful. I mean, given that humans use multimodality, but if, for example, suppose you go to a doctor and you have issues with your you don't breathe well and so forth, I mean, the doctor will most likely order exams that utilize maybe scans. They typically utilize radiology notes. They take all this information intuitively and make a diagnosis. So the prior is that most likely would help, assuming you do a reasonable job. The question is, if it's so, and by how much? So we have found, without going to the extreme details, is that this is accuracy and AUC, the area under the curve is similar, that the additional characteristics. So the baseline is just electronic medical records, more classical machine learning. So this is sort of the baseline. The baseline is what we do more or less today, by and large. We have found very significant improvements in mortality, in classification, and length of stay. To be honest, I wasn't expecting the level of improvement we have observed. And in addition, not only the accuracy improved, the variability of which is also relevant sometimes, the variability of the prediction also improved. Just to indicate that this is not just in the theoretical realm, I would like to give you a test case where we actually utilize this in a real world environment. And the environment is the Hartford hospital system, which is 7 hospitals in Connecticut, the largest system in Connecticut. It's a sizable place. They have 2,500 beds in 7 hospitals, about a revenue of about $5 billion a year. And as I mentioned, the largest hospital system in Connecticut. And the topic is, we built an application that doctors use. So on a daily basis, early in the morning, this data is available for all patients in the hospital, including structured and unstructured. So this methodology runs and makes predictions about length of stay, mortality, ICU utilization, and so forth. It doesn't yet is used for diagnosis, but is used for the functions of a hospital. And what we have found, this is relevant. For example, discharge is particularly relevant for throughput considerations. If you are able to, if let's say the average length of stay is 6 days and you make it to 5 days, because this is a high throughput hospital, you can now increase your throughput and therefore serve more patients by 1/6 more, 15-16% more. Many other applications, mortality, for example. Why is it relevant? Because if you have a patient, the machines are better than humans in detecting things because they have a lot of data. So in fact, multiple times we have observed that they can detect the deterioration of a patient far earlier than humans, thus saving their lives. I have multiple anecdotal evidence on that. Multiple others, I won't have time to say that. Across the board, the area under the curve, while not perfect, is pretty consistent in the 85% range. In mortality prediction is in the 90% range. So not only that, the models are reasonably calibrated. So if you say the predicted probability and the actual probability, they are well calibrated models. That's relevant because if the calibration is not fantastically well, it loses credibility. We have built a software system that runs within the hospital that gives you, for every patient, which is a row, it has a color. Red means high probability danger, high probability of mortality. Green means the patient is ready to be discharged, so therefore the system can indicate. And yellow is an intermediate category that we no longer use because the doctors told us simplicity is better. That's what they have decided. So this is in the end of the day, we have some efforts on interpretability. Interpretability is not, I think it's a major issue with deep learning. Interpretability is a difficulty in the story. We made an attempt at least to give you an indication of what are the signals that are most important. This is a subplot, but while I don't think it's perfect, it's a step in the right direction. We are currently working on improving. The most important is that this is an A/B test in which we have started 2021. We started implementing 2022 on 15 units. And this is the trajectory of length of stay after implementation. This is for the units that didn't have it. So I would say there's a delta of about 60.67, 2/3 of a day of improving length of stay. That's not negligible. I mean, of the size of this hospital system, being able to improve by that level is, makes a material difference, both from the perspective of serving new patients and increasing revenue for the hospital. We estimated that this is of the order of $50–60 million a year increased benefit on that. Some of it has been already realized because of this structure. The point of this is the following, is that the additional data appropriately composed in a machine learning method. I'm not claiming that this is the only method or the best method, but I am claiming that multimodality is helpful. So that's the point. Since then, we have applied this to multiple other examples. We have a nice collaboration with the Brigham and Women's Hospital in which we utilize this data for detecting domestic abuse. I used to think that domestic abuse is a third world problem. It's not. It is a first world problem. It is a third world problem. It's also a world's problem. The Brigham and Women's Hospital nearby is definitely in a first world environment. And being able to detect it because you have images, you have interviews and so forth, multimodality is particularly helpful. It adds another 10% of accuracy just on tabular data, and many others. In fact, we have recently initiated a projects actually 15 of them at the Hartford Hospital System, where we utilize HIME, Holistic AI for Medicine, for a variety of applications, understanding brain cancer, understanding psychiatry effects, and so forth. And I think the applications of this area are still in many things in the future. So this is sort of my first point. Very briefly, I would say that we have applied also this around this time. We have published a paper to a meteorological journal, a very high quality one, weather and forecasting. Fair to say, while I have a lot of experience in medicine, in meteorology, I'm a complete novice, meaning I know nothing. The only thing I know, I'll tell you in a brief moment, which does indicate, you see the results are, in my opinion, very impressive. You can improve the state of the art in this area. I believe this is a lot to do in this area. So the overall idea of the model is to predict direction of hurricanes as well as magnitude of hurricanes. This is, in a world that has global warming, this has been worsening. I mean, this is it's at the level of existential crisis for humanity. So the data we use is the data that is funny. Huh? You see these aeroplanes that go near hurricanes, and I always thought they were crazy to do. I still believe they are crazy to do that because they are endangering their lives. But they have collected a lot of data about pictures of hurricanes. We have data for about 3,000 historical hurricanes. This is publicly available data. It's not private. Difficult to find. We also have historical features. We have meteorological data, and we also know what happened. So this is short-term prediction within the next 48 hours, which is particularly relevant if you are going to make some decisions. We utilize the methodology of embedding similar things, and we have found that the accuracy of so these are national models. So this is the error, the mean absolute error of the national models used today about hurricanes is about 10.6. The units are this is in the Eastern region and the North Atlantic in kilometers. We are obviously comparables, in this case better, in this case worse, but that's not the most important thing. This does not use PDEs. This just uses multimodality. This is use the classical approach of what we teach in physics departments, in the mathematics department, where we use Navier-Stokes equation numerically solved with fantastic solvers. This is efforts that have been around for more than 100 years, and they are used today. And this is somebody, 3 students and a professor who none of us knows much methodology, just using multimodal AI, you can do that. But that's not the most important thing. The most important thing is you combine them. I mean, you use the experience. Multimodality could mean PDEs. So we use that, and it's about 15% better than the current prediction. So I think it's ready for national use, I would say. And this is not this is somewhat of an amateurish implementation. We wrote a paper. We did not, I would say if we have experts doing it, better things can happen. I hope I have at least convinced you. Since then, we have done other applications in agriculture and so forth. But I think the opportunity is significant. It's early phases as well. Given that the audience is of young people, I would recommend you take a look at this area. There's a lot to accomplish, lots to accomplish. I honestly believe that. I mentioned some others. Some of them I'm working, some of them are not. In my home country, in Greece, in the summer, there are a lot of fires, right? I mean, lots. I mean, where I was born, in the northern part of Greece, in the summer, we had one of the best forests in Europe. It was all gone. I mean, really, it saddens me to think about that. I grew up in that environment. So I believe multimodality is relevant there. That is, you have satellites, you have sensors, and so forth. I haven't worked on it, but I think it's an opportunity. So now, and many others that I can think of. So what I would like now to talk in the last maybe 6-7 minutes that I have, until 9:30, but 9:34, So. It's something that I think it's, I have been an educator for 40 years, all my life here. So obviously I care about education and universities, particularly this one. For example, MIT is organized for about 70 years in 5 schools. Now Schwarzman, where we are, is more horizontal, right? So, but we have 5 schools. The Sloan School, where I come from, it started about 70 years ago. We have science, engineering, humanities, management, and architecture. Recently, we have added a version of horizontal. Each department is structured also hierarchically. The engineering department has ECS, has mechanical engineering, and so forth. This reflects the current history and the current tradition we have. Also, change in academia is difficult. For those of you that have been in a position to attempt to change, is one of the most difficult things. And I have tried over the years to make some changes, some of them successful, some of them unsuccessful. And the major reason is not necessarily the rationality or how good the idea is, it's also the political landscape. Given that the young people in the audience don't fully understand what I'm saying, but I'm just preparing you. Change is difficult. It's not an easy task. However, this structure that we have, is this the optimal structure nowadays, or should be adapted? Clearly, you can expect that my answer is the following. Also, real-world problems do not have labels. The global warming is not a physics problem. It's not an engineering problem. It's not a mathematical problem. It's a problem. Medicine is not a biology problem, it's not a chemistry problem, it's not a computer science problem, it's a problem. They don't have a label, they don't naturally belong to a particular area of knowledge. And given that the data is in electronic form, structured and unstructured, at least it makes sense to me to utilize all the available data for better decision making. Rational people, it's very hard not to agree with this statement. But here are some reasonably safe predictions. I believe that multimodal data will increasingly be used in science, engineering, and medicine. It's already on the up, early phases, but I believe that's a safe prediction. I also believe that multimodal machine learning, which is still early phase, we don't have a class on multimodal AI today at MIT that I know of. There's a computer vision class, there is a large language model class, machine learning classes, and so forth, less so on the subject. It is my view that because of its power, because of its applicability, it is going to become the predominant methodology for predictions and decision making in all fields. All fields important, not just medicine, agriculture, law, and so forth, in all fields. So as a result, I expect that universities in the future will be organized horizontally in the direction of the Schwarzman College, but a step further, not just an administrative structure. What do I mean by that? I mean, last summer, I have offered a class in Greece with I call it Universal AI. Universal AI had 500 people present, because that's the capacity of the auditorium, and about 1,500 people remote in Greece. These are all, the audience were law students, medical students, engineering students, mathematics students, all fields. Universality was in the audience as well. And most of them did not have a lot of understanding of this. This was a 3-day morning to night. It's roughly 20 lectures, myself and another colleague, and it is fair to say it affected the trajectories and lives of some of the people. I cannot say, because for the first time in their lives, in the same room, they were with a physicist, a mathematician, a lawyer, and these are young people, many like yourselves, a bit even younger. And what I have observed, and since then also, that it has changed their perspective and so on. So it is my view that this is an experiment that would be worth doing. MIT is tougher to do. You know, I have white hair now, as you observe. I've been here for a long time. Changing a place like MIT directly is tough, even though, you know. So I experiment first on things that I control better. So we have started this in Greece. We have started this in a university in Morocco. And we have existing environments. We have 4 horizontal classes. One of them is multimodality, classical machine learning, prescriptive AI, multimodal AI, and some applications overall. And then vertical, the vertical we are not there yet, AI and physics, AI and this. So everybody here has taken a calculus. All of us are STEM, I bet all of you are a STEM background. So what is considered obligatory is calculus, right? Everybody has taken a calculus, no? Have you taken a calculus, my friend? I'll be shocked if you didn't take a calculus class. So my view is the corresponding calculus for everything, not only for STEM, for the future is AI, particular multimodal AI. That's my belief of the future. As a result, I would say we should create the structures, even restructuring our educational system, that to consider. MIT as a place doesn't have a law school, doesn't have a medical school. Why not? If we structure on our strengths, I see no reason, but we won't call it a law school. We won't call it a medical school. We'll say we educate people in digital sciences, digital medicine, digital agriculture, digital this and digital. And I believe we are in a good position to make a dent on the story. So that's my thoughts. I could approximately okay?